Hello and welcome to the AP Statistics video on the notes kind of concerning one proportion z-test. One proportion z-test. So the idea, like, this is kind of an introductory prompt here. So Mr. Herzenberg says that 70% of the parents would like to remove all the drink machines from campus. Mrs. Bennett is responsible for getting rid of the soft drinks in the machines recently. The last couple of years she did that, a few years ago. But let's just say that 70, like Herzenberg says he wants to get rid of the machines. So he says 70% of the parents would like to remove all the machines, just remove all of them. All right. So what are you going to do if you want to keep the machines around and you don't want them to do that? Well, in stats, you would, as a mathematician and a statistician, you would go and do a sample and find out the truth, or at least try to find out the truth. So we're going to get back to this problem after I go through all the little things you need to pay attention to, and then we'll go through the problem and see how it all applies. Okay, so let's jump to some of the actual notes. This is a hypothesis, and the whole idea is you are testing a hypothesis, and we're doing just proportions today. You can do the same thing for means, but this is about proportions, right? So what percentage of people or what percentage of things. So the hypothesis is usually a claim, something you read or something somebody said, or someone's claiming something to be true and you want to test that claim. So we call it a test, testing the hypothesis that somebody's claiming. We have a null, that's the null hypothesis, that's what the claim is. So it's what somebody says to be true, then we're going to call it the null hypothesis. And we're going to use this little H naught to kind of represent that right there, right? Okay, we call it H naught, right? So that's our parameter. We're gonna assume this is true to begin with. So it's kind of like if you take someone to court, you kind of assume they're innocent to begin with, and then you try to prove that they're guilty. Same thing here. We're not gonna call Mr. Herzenberg a liar ever, but we will kind of assume that he's true to begin with, and we're gonna use our statistics to try to disprove him. So we're gonna assume this 70% is the actual truth, and then work from there. Okay, so that's why it says it's a parameter. So it's the hypothesized value. All right, then, so what we're trying to prove then is what's the alternative? What's the alternative to that? Well, we think it's less than. So you have some options. You can either say it's less than, it's greater than. I think that's on here. Yeah, it's either less than or greater than or not equal to. Those are our choices, right? Sometimes we really are concerned that it's one way or the other, but sometimes we just don't really care if it's less than or greater than. We just want to know if it's different. So if you're reading a question and it doesn't, like, you have to look for the wording, right? To say, does it say less than? Does it say greater than? Or does it say just different? If it just says different, we're going to use the both direction kind of alternative. So again, the alternative in this case, when we talk about Mr. Herzenberg problem, the alternative is that we think it's less than that. We don't think there's that many parents who really want the machines to be removed. And hopefully if we can prove it, then we can talk Mr. Herzenberg into not removing the machines, right? That's the idea. So that's our alternative, the alternative to the null. All right. We think the probability is either less than, greater than, or just different than what the probability says. So this is kind of a visual of that. If you say it's less than, then you're going to get this first graph, right, where you're looking at some cutoff value. Now this would be the claim. We always make the claim the center, and then this is what you're going to get from your sample, right? This cutoff here is going to be what you get from your sample, and the whole idea is that if this really is the truth, and then you do a sample, how unlikely is it to get a sample that you got just from randomness alone? Because remember, we're assuming this to be true to begin with, and we're going to take a sample from that population and get some result. So we want to say, well, is this result I got from my sample so unusual that I think this truth is actually not the truth? Or this is the sample I got kind of what I would expect. Like, if this was the truth, then I would expect to get a sample like this once in a while. Because of course there's variation, right? Sometimes you get a sample that has a proportion a little bit bigger than what what the truth is, and sometimes you get a sample that has a proportion that's a little bit smaller than what the truth is. We expect that. We don't expect to get the exact same proportion as the whole population every time. But the big question then is this sample I got within that range of what I would expect from just variation, from randomness alone? Or is this value I got so unusual, like it's so far away from the truth, or so far away from what I thought the truth was, that I'm actually going to start to believe that this probably isn't the truth because this was so unusual. I shouldn't have seen that. So if I am seeing it, I'm assuming that then this becomes a little nebulous, and you start to think maybe this isn't true. So we're going to reject that hypothesis if we think this is really, really far away. What you got from a sample is so unusual. So for a one side, it looks like this. You're just going one direction or the other. It could be in the upper end. Sometimes you don't really care, though, that it's less than or greater than. You just want to know it's different. So is it bigger or smaller? What's the probability of finding something that unusual in either direction? So really, the probabilities that you get from your answer are just going to double, pretty much going to double from what you would have done on a one-sided or a one-tailed test. All right, so there's examples here how to set them up. We're going to do these one by one. So number one, you read an article that says 64% of the people in Tokyo think that drinking age should be lowered to 18. Wouldn't some people really like that, right? It's 20 now, and some people want to lower it to 18. Heck, you can join the military when you're 18, right? They think you're an adult when you're 18. Well, in the States they do, right? In Japan, I think is more 20, right? So the drinking age kind of matches, the coming of age, right, when you're 20. But anyway, you believe it's less than this. So you think, like the Article 6, 64% of the people want to change the drinking age to 18, but you think it's less than this. So how would we test this, right? How do we set this up? Okay, so as a basic setup, usually you're going to follow the same pattern. You're going to represent, like tell us what you're doing, maybe define a variable. So it doesn't have to be P, but a lot of times we use P for proportion. So let P represent the proportion of people in Tokyo that think the drinking age should be lowered to 18. So I'm kind of just restating it, but really what I'm doing is defining a variable. Okay, we have H sub O, which is H naught, which is our null hypothesis. Notice I'm using P naught as well to represent what the claim was, right? So the null proportion is 0.64. And keep in mind, we're going to assume this is true to begin with, okay? The alternative, what you think, is that, like the P alternative, is that the proportion is less than 0.64. That's what you think. Now we have to set this alpha. This alpha is your significance level. And it talks about it in the notes later on here. But that needs to be set ahead of time. You're not supposed to set it later on when you get your result. You're supposed to do it ahead of time. And usually we use 0.05 because what it says is that if my result, like when I get done with this, I'm going to get a probability, right? I'm going to have an area and a probability of what I see happening. Like what's the probability of this happening? So if my probability is really unusual, then I'm gonna tell that claim, or I'm gonna say that this is probably not true, and I'm gonna say we need to do more research, or I'm not gonna flat out call him a liar, but I'm gonna say I don't think this is right. I don't think it's true. So before I can do that, I need to know how sure do I want to be before I start telling someone that they're lying or that this is not true. Well, usually 5%, right? If there's less than a 5% chance of something happening, but it actually does happen, then you're going to say, wow, that was really unusual that really it happened, even though I didn't think it was, like, it shouldn't. If this was true, then it shouldn't have happened. But if it's something really, really important, then you want to be really, really sure before you say this is false, or before like, you make big decisions based on this. So something like maybe you're going to, I don't know, make a new building, or you're going to invest money into a business, or you're going to change the way your business does business. You're going to change something that costs money and costs time. You maybe hire more employees, or maybe you're going to fire people, stuff like that. So there are some big decisions out there that could be based on this. So maybe you want to be really, really sure before you make that big decision. Then maybe you want to lower this number from 5% down to 1% or something low, where like you want the result to be so unusual that you're almost positive that you want to make the change, right? So you'd want to make this smaller. If you don't care so much and you just want to have some evidence it's not really that important, or there's not big consequences, then maybe you could raise this up to like 10%, maybe, right? But usually we use 5%. It's in AP statistics, we use that a lot. Okay, so let's say I do a sample then. So I've kind of laid things out, and then what you do in the real world, of course, is go get a sample then. So I'm going to randomly select people in Tokyo, and I'm going to ask them if they think that drinking age should be lowered. And then let's say I surveyed 108 people, and 59 of them said they do think that it should be lowered. All right, so that gives me a proportion of 54.6%. All right, so to go along with that, I need my standard deviation. Now, here's the weird part. We don't use the standard deviation from the sample. We actually use the standard deviation from the null hypothesis. Why? Well, because I'm assuming this is true to begin with. So if this is true, then the center of my normal curve is that null, and the standard deviation I should be using comes from the null. It doesn't come from my sample. The sample proportion is just something I'm using to test how unusual, like, or if this is what, like, I'm testing my sample proportion, right? From the null though. So you can see here I got the 0.64 and 0.36. I don't use the 54.6, and I get my standard deviation that way. All right. Now this is just the first part of 4 parts when you do this type of problem, and we're going to see the rest of that in a minute. But there are 4 parts to this. But the setup is really, really important. Well, all of it's important, but there's a setup. So let's see some more setups. Okay, so the second setup, Ford believes that 2% of the engine mounts that are manufactured are defective. They're wondering if it is higher than this. If you want, you could pause the video and try to write this setup yourself before I show you the answer, okay? I'll show you what I would do. So pause it if you wish, and write the introductory part just like I showed you on the last one, and see if you can do it. Okay, so after you paused and you've tried this on your own, Ford believes 2% of the engine mounts are manufacturer defects. You wonder if it's higher than this. So this is how I would set it up, right? Define your variable, Ford engine mounts that are defective. Your null is the claim of 2%. You think it's higher than that. Notice I'm using greater than symbol now. And I'm going to keep my alpha, or my significance level, at 5%. And from my sample, now I just made up a sample. You have to make up your own sample because they didn't really give us that. But let's just say I got 7 out of 300. I went and I randomly selected 300 engine mounts and tested them to see if they were defective, and I got 7 out of the 300 that were defective. So this would be my proportion for my sample. So you can make up whatever you want because they didn't say anything, but in the real world you would know, right? And real problems you know. Now the standard deviation part, you have to use the 0.02. You can't use the sample that you had. Okay, so that gives you 0.008 for your standard deviation. Everybody should have that same number if you did it. Okay, here's another one. Company claims that their pain relieving drug works on 75% of the people who take it. You experiment to see if the true proportion is different than this. Now notice the wording here. I did this on purpose, of course. This is less than. This one's higher than, so that's greater than. And then this one just says it's different than this. So if you see that, that should tip you off that it's a not equal situation. It's not greater than or less than. It's just not equal. All right, so set that one up if you wish. Pause the video, and I'll give you the answer in a second. Okay, hopefully you're back and you've written it all up on your own. This is what it should look like. You define your variable. Null hypothesis of 0.75. Alternative is that it's not equal to 0.75. So that means it could be less than or greater than. It's both. So your probabilities tend to get doubled from what you would do on a one-sided one. Keep the significance at 0.05, no reason to change that. I made it my own sample, but for your standard deviation, you should be using 0.75 and the 0.25, and that gives you 0.061. All right, if you need to go back to these, of course, you're on video, so you can go back and watch it if you need to see it some more. All right, let's go look at the rest of these. So what's the final goal? Well, the final goal is the p-value. What's the probability of seeing what we're seeing? On a graph, you're looking for the red areas, right? You're looking for those red areas. That's the final goal. If your p-value is less than your significance level of usually 0.05, so if your value is less than that, then you're going to reject the null. You're going to reject it, and you're going to say, I don't think that null hypothesis, that claim, is true. If your p-value is high, it's a 50% or 40% or 30%, then you're just saying, well, that happens, like the sample that I got, that type of sample happens 30% of the time or 40% of the time, so it's not unusual. So there's no reason to think that the claim is false, and I'm going to accept that claim, or at least I'm going to say I failed to reject it. I don't have any evidence to suggest that it's wrong. If you do reject it, then you're going to say, I do have evidence to suggest that your claim is wrong. Now, that doesn't mean they're liars. We in statistics, you don't call them liars. You're not 100% sure, right? You're never going to know the real truth, but you have evidence to suggest. So either you don't have evidence to reject it, or you do have evidence to reject it, all right? So we kind of talk in those terms of evidence. All right, so we've already looked at this, and notice here how they use P naught and Q naught. They're not using P hat, Q hat. And then also we can get our z-scores. You're going to take your sample proportion minus the null in order to get your z-scores when we do these probabilities. And then here's where it talks about the significance level alpha, right? Alpha. We're setting our alpha. All right, so we've got a couple problems. Let's go back to Mr. Herzenberg's problems, and then we'll be done. We'll do 2 problems, and then we're done. The video will be finished. So back to this problem. So he said 70%. So when I set it up, I should have 70% as my claim. Of course, I define my variables, and then I think it's less than 70%. I leave my alpha at 0.05. Now, let's just say I go do a sample, and I get 28 out of 50 for my sample out of the ASIJ parents. I went and surveyed 50 ASIJ parents. 28 of them said they want to remove the machines. Well, to me, that comes up to 0.56. So some people might immediately, like some people in the real world, without knowing statistics, someone says, oh, it's 0.7, 70% of the people want it, and then you do a sample and you get 56%, and you just start calling them liars. Well, we don't do that in the real world. Well, in real statistics, we don't do that. Real world people do it all the time, right? But yes, there's a difference. I can see there's a difference between 0.7 and 0.56. So maybe it really isn't 0.7, but maybe this 0.56 just came about because of the randomness in my sample. Maybe I just happened to survey people who did want the machines or who didn't want the machines removed. All right, so that's why we do the statistics, to kind of get a better idea and look at the probabilities to know how unusual it really is. Okay, so I do my standard deviation based on the null, and I get 0.0648. All right, now notice how I set this up in a 4 cross. I want you guys to do this like the rest of the semester. You're going to be doing lots of this. All right, the first section is to set it up and kind of lay out your test or get your statistics and just kind of set it up, define variables. The next section will be for your conditions. So before I can use a normal model, I have to check my conditions. Once you check your conditions, down on the bottom left, I'm going to do my work with my normal model. I'm going to draw a normal curve. I'm going to get a z-score and come up with my probability. And then, of course, you always have to interpret your results. So this last quadrant is to interpret your results. So when you enter a problem, make sure that you're putting this, you don't have to actually draw the cross, but if you have that cross in your mind, it'll remind you to do the 4 things. Define your variables and set it up, check your conditions, do the actual work and get your p-value, and then you still have to put it into context and make some sense of what you came up with. Okay, so what would that look like on this problem? Defining your conditions, or not defining your, checking your conditions. We go through IRS 10, right? You got to make sure that there's no reason to believe there's any dependent situation going on. So I check that. Parents are randomly surveyed, so I check that. On the proportion ones, you have to go your sample size times P and your sample size times Q in order to end up with, to make sure that your sample sizes are both bigger than 10, like your successes and your failures are bigger than 10. We also just have to do a quick check that our sample size isn't too big, so that we're changing probabilities. We don't want to change probabilities. So yes, 50 is less than 10% of the thousands of parents that we have at ASIJ. Okay, and then the next section is then doing the work. Once we've checked our conditions, we're allowed to do a normal model. So you can see here I said conditions are met, so we can use a normal model. I draw out a normal model, I label it, I shade it in, I calculate my z-score. This is back to what we used to do. Now keep in mind, you're using the standard deviation from your null. You're doing that down here in your z-score formula. So be careful of that. It's a little bit weird. And you get a negative in this case because you're to the left of the center. And then you do your p-value and you get 0.015. Now to do this work, you can use your calculator. It has a nice little testing feature for you. And let's check it out. Oh, I did it right there. Is this the same problem? So I got 0.7 is my null, and I did 28 out of 50. 28 out of 50. So you can see right here, I've already done this, but let's do it again so you can see on the calculator. So when you get in here, the statistics, down here, it has confidence intervals, and then you also have your stat test. And this is a 1 proportion z-test that we're doing right now, 1 proportion z-test. It asks you what's your null, so I put in my 0.7, and then we had 28 out of 50, right? So I made up that, but 28 out of 50 people said that. Now you have to pick, is it greater than or less than? In this case, we think it's less than that. And then you do your results. It'll give you your z-score, 0.216. So you can check your work, right? 0.216. And then it also gives you this p-value. That's the shaded region here that I shaded in blue. So that's 0.015 in this case. Okay, 0.015. All right, so I like to kind of do it by hand and then use my calculator to check my work and make sure I got the right number. That way I know if in my writing I made any mistakes. Okay, but that's all you need to do there. I got my p-value. That's kind of my goal, is to get that p-value. What's that probability? Now I can see right away this is a low probability. So this sample that I got, 28 out of 50, it really was unusual. Like, it's unusual to get a proportion sample of 0.56 if the truth was really 0.7. So I really do think that 0.7 is probably wrong. All right, so let's write that up. You got to say that. Since our p-value of 0.015 is less than 0.05, so I'm just comparing my p-value to my alpha. And this is where that alpha is important. If I would have said my alpha was 0.01 in the beginning, this would totally change my result. I would not be able to reject the null hypothesis. I wouldn't be able to reject that claim. But now, since in the beginning I've set my alpha at 0.05, then I can say, well, yes, my p-value of 0.05 or 0.015 is less than 0.05. So I'm going to reject that null hypothesis, and I'm going to go to Mr. Herzenberg, and I'm going to say, you know what, your claim, I don't think your claim is true. I think it's lower than that, because I got 0.56 in my sample, which is lower than 0.7. So I think the truth is, I don't really know if the truth is 0.56, but I'm pretty sure it's lower than 0.7. All right. So notice how I said we have evidence to suggest. I don't call him a liar. I don't say he's wrong. I just say, I have evidence to suggest that the true proportion is less than what you claimed. Right? The real kicker is that in the real world, like in the truth you're never going to know. You're never going to know unless you do a census. So this is the best we can do. We can just say, I have evidence to believe that you're not right. So let's investigate further, and before we make any decisions, right? That's just the best you can do. Okay, so there's a full write up. That's what you have to write on a free response question. That's what it should look like. All right, I think we've covered it all. Last problem. I'm just gonna put this up. You can read it. You can try it, and then like pause the video and try it, write it all out, do the 4 corners, make sure you cover all 4 sections like we did up there. And then I'll give you the answer here. So pause it, work it. All right, you shouldn't be looking at this unless you've done it on your own. Did you get something like this? I hope so. So you set up your null 0.9. From your sample, you got a 0.94 as your sample proportion. We use the 0.9 to get our standard deviation. So that gives us 0.015. Check your conditions. You'll notice that I put the independence and the randomness together here. A lot of times I do that because they go hand in hand. If I randomly select houses, there's no reason to believe that one is dependent on the other. That if you randomly select the houses, they should be independent of each other with regards to smoke detectors. I check my results, or check my sample size, sorry. So there was 400 total, 0.9 times 400 and 0.1 times 400. I have plenty of successes, plenty of failures, so that's bigger than 10 each. And yes, 400 is less than 10% of all the houses in Chofu. There are thousands and thousands of houses in Chofu. Okay. And then we can go on. So conditions are met. I can use a normal model. I draw it out. I get my z-score then. Remember, the z-score standard deviation comes from the null. So 2.67, I can tell right away that's a really big standard deviation. I know this is going to be a really low p-value, which it is, 0.0038, really, really low. That's definitely less than 0.05. So I have evidence to suggest the true proportion of houses with smoke detectors is higher than 90%. Notice I did use higher in the beginning, so all this is based off of higher, right? Okay, that's it. Look for more problems to work, AP problems and whatnot, stuff we do in class to get more practice on this.